In this lecture, we're going to look at the various types of intermolecular interactions, starting with, I mean, some of these will be fairly fundamental, and if you had a pretty robust Gen Chem or high school experience, you will see, many of these will be familiar, but they're at least worth talking about. So I'm going to kind of go in order of strength and that sort of thing. So the strongest intermolecular force is going to be the ionic / electrostatic interaction. And this is kind of what I mean by strongest. This is just kind of the strongest one in terms of the fundamental one. So if somebody's out there saying, well, we've discovered a new, stronger intermolecular force, sure. And really, this isn't even much of an intermolecular force. It's kind of an interatomic force, but it gets cumbersome when you get multiple of these atoms together. So the ionic or electrostatic interactions is kind of talking about ionic bonds. And you might say, well, ionic bonds, is that really inter much? Well, if you look at NaCl, it's really sort of an arrangement of Na plus atoms and Cl minus atoms. And if you actually look at an NaCl crystal, you'll see the atoms alternate over a lattice. That's how you get these salt crystals, sodium chloride crystals, is you form this regular array of elements or a lattice. It's a bit beyond the scope of the class to go too much more into detail on that, but let's just suffice it to say I've got a temperature in my notes of 1,413 degrees Celsius, which is a really high temperature. And let me just see what phase transition that is. I'm just not even going to take a guess. So the boiling point of sodium chloride is, yeah, okay, it's this. So this is the boiling point. So with sodium chloride, you have such a strong interaction between the various sodium chloride compounds, ionic salts, because the sodium is forming an electrostatic interaction with the chlorine next door, and then the chlorine next door, and is this chlorine part of that sodium, that sort of thing. They're all just kind of in this regular array together, and as a result, they're very tightly stuck together. And so we'll see the boiling point then be almost 1,500 degrees Celsius or 2,700 degrees Fahrenheit for context. But again, these interactions are a bit beyond the scope of the class, but it's important to be aware of these types of interactions, ionic, especially in the context of the ones that we're actually going to be using quite a bit. And the one that is sort of next on the list in terms of strength are the dipole-dipole interactions. And these are the ones that are, it's hard to just call something most interesting because these are all interesting in their own way, but this is the one we're going to be taking advantage of the most experimentally and theoretically, sort of going forward. So in dipole-dipole interactions, we're going to have a molecule that I'm just going to designate as A and B. And let's say that A is a bit more electronegative than B. And so B is delta positive because it's electropositive, A being the more electronegative element, which I'll label as En. A is going to kind of hold on to the electron density a little bit more in that covalent bond. And we're going to see a dipole form where the electrons are sort of shuttling over to A. Now, what happens is if you put A and B close to another AB molecule, the delta minus on the neighboring AB molecule will feel the effects of the delta positive on the neighboring B atom from the other AB molecule. And they'll start to form an interaction, which I show as a weak line. So this is an interaction that is attractive. I should have written that as attractive interaction, not interaction attractive. It's a bit awkward. Okay, so we have some sort of attractive interaction. And I draw it as a dashed line because I want to make sure that I'm clear. This is not a bond. There's not a sharing of electrons across these two elements. It's just the fact that we have a delta minus and a delta plus, and they feel each other, and they're going to stick to each other. And this stickiness is an attractive interaction across different molecules of the same type. So it's attractive and it's intermolecular. This is a classic example of an intermolecular attractive interaction, and probably one of the most important ones. So this will increase the boiling point of A and B. A and B. And so it turns out that this attractive interaction is really pronounced in an interesting way. If you recall, we had looked at the boiling point trends for the alkanes. You can do the exact same thing for alcohols. Like you could start with methanol and show that it is lower than ethanol and show it's lower than propanol, and so on and so forth. More carbons increases the boiling point. Now, what you notice is if you compare methanol to methane, methanol's boiling point is much higher because it has an OH and has an opportunity to do another type of attractive interaction, which is a dipole-dipole interaction. But as you go from methanol to ethanol to propanol, you're adding carbons and you're increasing the boiling point. If you actually delete carbons in methanol and go to 0 carbons, well, what's a 0 carbon OH alcohol containing molecule? A 0 carbon OH molecule is water. So water has, instead of a carbon attached to its OH group, it has a hydrogen. So it's just H2O. Well, water has the opportunity to form, I'm going to move on to the next page of notes. If we look at water, water has an opportunity to form two dipole-dipole interactions. It has a delta plus on a hydrogen, a delta minus on an oxygen, and another delta plus on the opposite hydrogen. We have dipole arrows moving into the oxygen atom from two sides now. So we have the opportunity for two dipole-dipole interactions. That is, this hydrogen could interact with an oxygen atom on an adjacent water molecule, and this hydrogen could interact with an oxygen atom on an adjacent water molecule, and the oxygen could interact with a hydrogen on an adjacent molecule. And so what we see is there's more opportunity for hydrogen bonding, more opportunity for dipole-dipole interactions. And what's very interesting is that water's boiling point of 100 degrees Celsius, a very good number to know, water's boiling point is actually greater than that of methanol and ethanol. So even though those have infinitely more carbons, I guess, from 0 to 1 or 0 to 2, but because they've got even more carbons, you by having an additional opportunity to form a dipole-dipole interaction on both sides, you're going to see an increased boiling point. Now you might say, well, our carbon and oxygen, the one you keep alluding to but not drawing in your notes, that's a dipole, right? I mean, oxygen's more electronegative than carbon. Well, hydrogen's quite special because hydrogen is so electropositive and so small and accessible that you're going to form an actually quite strong dipole-dipole interaction, and it's called the hydrogen bond. This is a most famous / important dipole-dipole interaction. Okay, now what's happening here is you've got some electronegative element attached to hydrogen. So you have a delta minus on the electronegative element. Then you're going to have an interaction between hydrogen and other electronegative interactions, and the electronegative element and hydrogen from another molecule. So when one of the elements that's interacting in a dipole-dipole interaction is hydrogen, we just call it a hydrogen bond because it's so important. So one interacting element is hydrogen. And we'll talk about these more when we talk about soap. So, you know, I want to move on to the next force, but I don't want to undersell this. Hydrogen bonds are so important. It's such a pronounced and interesting dipole-dipole interaction. It's everywhere, especially in biology. When we talk about DNA, one thing that should come to mind is the idea of a double helix. So not thinking too much more than we need to about the double helix, but the double helix is critically important for the stability of DNA and our ability to kind of replicate cells and that sort of thing. The double helix, where we're taking one strand of DNA and attaching it to another strand, the links between the two strands are actually hydrogen bonds, and they're so strong and so durable that they can kind of survive a lot of the punches that cells take, assuming that we're packed up inside the nucleus of a cell. But then during cell replication, when we need to have the DNA accessible so that it can be copied, those hydrogen bonds, because they're not covalent bonds, we're not like pushing electrons around, they can just split open as needed and then come back together. And what's cool about DNA is they kind of build a puzzle piece for each of the nucleotides. So A always wants to bind to T because A and T form two really strong hydrogen bonds, and G and C form three really strong hydrogen bonds. But it's like a puzzle piece where if you try to put a 2 piece with a 3 piece, it doesn't match, or 3 of the same piece, it doesn't match. Really just interesting feat of biology to accomplish this. But it's all using hydrogen bonds, these really strong intermolecular interactions that are dipole interactions that happen to have hydrogen present. Okay, I said I wanted to move on to the next interaction. So we have ionic bonds or electrostatic interactions, and these are not as strong as dipole-dipole interactions. And the least strong, but one that we should talk about, are the London dispersion forces. London dispersion forces. And so these are the dominant interactions in nonpolar molecules like hydrocarbons or alkanes. So again, let me rephrase that. These are the dominant interactions in nonpolar molecules. Like alkanes. So this first functional group that we want to look at, the reason why we're talking about these intermolecular attractive forces is to just get some context. Dipole-dipole interactions are so important. Ionic bonds are worth mentioning, but London dispersion forces are the most relevant to what we're looking at. And so I said that alkanes are nonpolar molecules, and that's because carbon and hydrogen have roughly the same electronegativity. We're not going to see a dipole across most carbon-hydrogen bonds unless something else is happening within the molecule. And so we say that, like for example, methane has no permanent dipole moment. Okay, but that's a really important word, permanent. Now with London dispersion forces, we're going to see transient or temporary dipoles. Temporary/transient dipoles. So the gist of this is that if you've got, let's have two carbon atoms, okay? Just to emphasize the similarities in electronegativity. Okay, if we've got head-to-head overlap of sp3 hybridized orbitals to give us the molecular orbital. So this is sp3. And let's put an electron here, an electron here. And now we're going to form a molecular orbital. Form a molecular orbital if we have something like this, where now we show just one lobe as these things have sort of aggregated together, if you will. The electrons can exist anywhere inside this orbital, and they sort of move about. There's parts where there's higher density of electrons or lower density. For this, it's helpful to think about them as particles. They sort of exist in this duality, more like a cloud than a particle. But anyway, let's say the electrons are moving around and they decide to temporarily, they sometimes move over to the left side of the molecular orbital. So sometimes it's a probability that the electron density would be more positioned over the carbon element on the left and the carbon element on the right. That's going to create a delta minus and a delta plus, a delta minus of partially negatively charged species on the left carbon atom. But then other times it could be over on the right. These things are moving around, and as they move around, delta pluses and delta minuses are fluctuating, getting bigger, getting smaller. And what's happening is these temporary, short-lived, they're going away pretty quick. As fast as they're formed, they go away. But this like flux of sometimes we have charges on the left, sometimes we have charges on the right. All of this charge shuffling is creating small temporary attractive interactions between the molecules. The movement of electrons creates small and temporary partial charges. So it's definitely not a +1 or -1 charge. If a delta plus and a delta minus in a permanent dipole that wasn't temporary or transient was like, I don't know, let's give it a number of like 0.5, half of a charge. This is like a tenth or 5% of a normal charge. And it goes away quickly. So sometimes it's sometimes it's +5%, and other times it's -5% of a full charge, and many times it's 0. But these charges are fluctuating quite a bit, and this creates an opportunity for an attractive interaction. It's not a strong one, and it's certainly not a permanent one, but it is one nonetheless. Let's see. Hopefully the colors don't affect us too much. Sorry. Okay. It's not a small one, or I mean, it's not a big one, and it's a temporary one, but it's an important one nonetheless. So what's important is to take away from this is that we have the opportunity for some attractive interaction, and this is going to raise our boiling point because the molecules are getting stickier. Now, additionally, more bonds means more opportunity for transient dipoles, and that leads to stickier molecules or higher boiling molecules, higher boiling points. So this explains the effect that we saw in the last lecture, where as we were adding carbon atoms, we saw an increase in the boiling point. Every carbon atom that you add provides another bond. Every bond provides an opportunity for more of these transient interactions. And as you have more and more opportunities to have small, short-lived transient interactions, you're going to have a stickier molecule. Now, it's not as sticky as you would see with hydrogen bonding or other dipole-dipole interactions, and certainly not anywhere near as strong as an ionic interaction, but it's enough to see a change in a boiling point. So every carbon increase in about 30 to 40 degrees is because we have more opportunity for London dispersion forces. Let me summarize that. I think that's worth mentioning. Pages of the paper I'm writing on is virtual, so there's no sense in being too conservative with it. But these transient dipoles are created by short-lived or kind of dispersion of electrons in molecular orbitals. And so this leads to an attractive interaction. And that's where London dispersion forces come from. It's an attractive force or an attractive interaction caused by the dispersion of electrons just as a result of existing in molecular orbitals. And so this is going to raise the boiling point. And this explains why more carbons equals higher boiling points. Because what you need is just more sigma bonds, more molecular orbitals around for electrons to move about in to create these transient dipoles. More bonds equals more London dispersion forces. Okay. Hopefully that is somewhat clear. So more bonds, more dispersion forces leads to stickier molecules leads to higher boiling molecules. So in the next lecture, I think this will wrap up the next lecture will wrap up the module. We're going to talk about soap. We're going to tie all of this together to talk about something practical. I have fun with it. Hopefully you do too.